Assalamualaikum and good day to everyone. My name is Roaz Afika binti Samsudin. Today, I will be presenting on my final year project on the effect of simulated body fluid SBF on calcium silicate Chitosan composite cement scaffold, and I am supervised by Sir Henry Johan bin Muhammad Rizwan. To begin, let's delve into the background of the study. The importance of bioactive materials in bone repair has been well established as they can interact positively with biological environments. Despite the significant advancement, current bioactive materials for bone repair have limitations in its mechanical properties. For example, calcium silicate is highly brittle with a fast degradation rate that is faster than bone formation, hindering its commercial success. Next, understanding the behavior of composite cement scaffold when immersed in SBF leads to enhanced understanding of the material properties. To address this problem, several objectives have been outlined, such as to produce calcium silicate Chitosan as composite cement scaffold and to observe and analyze the bioactivity of composite scaffold immersed in SBF solution by using FTIR and SEM-EDX. Several studies have explored the role of calcium silicate and Chitosan in enhancing bioactivity. According to Liu, calcium silicate performs apatite rapidly compared to other bioglass and glass ceramics in SBF. However, it has drawbacks such as brittleness and rapid dissolution. Chitosan, on the other hand, forms stable structures in composite scaffolds and demonstrated strong fungi-static properties. Now, I would like to discuss the methodology employed to achieve the research objectives. Firstly, 5% of acetic acid solution and 1000 ppm of Chitosan solution was prepared. Next, the initial step of composite cement preparation involves mixing 9.5 g of calcium silicate and 0.5 g of alginic acid, which acts as binding agent. Two types of sample were made, which are calcium silicate with distilled water as control samples and calcium silicate with Chitosan as experimental samples, with respective solutions following a specified solid-to-liquid ratio as shown here. Next, the paste was poured in molds to get the shape and dried overnight at 60 degrees Celsius. After that, SBF was prepared to evaluate the bioactivity of the composite scaffold by immersing the composite scaffolds in an incubator at 37 degrees Celsius for different time intervals ranging from 7 to 14 days. Then, pH test and weight loss was assessed to determine the degradation rate. SEM-EDX was used to analyze the morphological and elemental composition of the scaffold surface to identify the formation of apatite layer, which is similar to the natural bone. FTIR analysis was conducted to identify the functional groups present in the scaffold to further confirm the formation of apatite after immersion in SBF. Next, I will be talking about the results obtained. First, let's consider the pH test results. Comparing the pH behavior of calcium silicate and Chitosan scaffolds, we see similar patterns: an initial rapid rise in pH, a slight drop around day 10, and a subsequent rise. However, Chitosan shows less pronounced pH changes and a slight lower final pH. According to Adrabo, the final pH in Chitosan composites was lower compared to bioglass due to calcium ions consumption during apatite formation. Next, I will be talking about the weight loss of composite scaffolds after 7 and 14 days of immersion in respective solutions. The weight loss of the scaffolds was calculated using the equation shown here, where W1 and W2 represent the initial and final weights of the scaffold samples respectively. The table shows that calcium silicate scaffolds in distilled water lost more weight than Chitosan scaffolds at both periods, indicating faster degradation. Similarly, in the SPF solution, calcium silicate also degraded faster than Chitosan at 7 and 14 days. The result is supported by Ching, which reported that crossings in the Chitosan composite scaffold form stable structures, reducing swelling and water uptake, leading to lower weight loss over time. It was also noted that the weight loss of the composite scaffolds when immersed in SPF solutions was higher compared to distilled water due to the buffer in SBF, which enhances the scaffold dissolution and calcium phosphorus layer formation. Now, let's move on to the SEM-EDX analysis. For calcium silicate in SBF, spherical granules appear on day 7, evolving into pseudospherical agglomerates by day 14, indicating an apatite-like layer. In contrast, distilled water immersion shows random particles with sharp edges and voids, indicating surface fracturing without apatite. For Chitosan in SBF, individual spherical granules form on day 7, indicating early calcium phosphorus precipitation, and by day 14, sparse precipitation is seen. Distilled water immersion also shows irregular particles, confirming no apatite formation. EDX testing confirmed these findings. For calcium silicate in SBF, the CAP ratio decreased from day 7 to day 14, indicating initial rapid calcium deposition followed by balanced mineralization. For Chitosan in SBF, the CAP ratio was 2.56 after 7 days, which enhances osteoblast addition, suggesting carbonated hydroxyapatite growth, which resembles natural bone and is more desirable than stoichiometric hydroxyapatite at 1.67. By day 14, the CAP ratio increased to 15.33, with phosphorus content decreasing over time as the CAP layer formed. This result is supported by Pang, which indicated that plate-like structures will form under lower ratios and increased surface coverage will form under higher ratios. Furthermore, the higher carbon and oxygen content in Chitosan suggests intact hydroxyapatite and Chitosan, enhancing mechanical strength, bioactivity, and controlled degradation. Next, I will be discussing the FTIR characterization of composite cement scaffold after immersion in distilled water and SBF solution for 7 and 14 days. The IR spectra were recorded with spectra ranging from 450 to 4000. All the samples immersed in SBF similarly exhibited bands located at 693 for siloxane, 563 for PO bonding, 3700 for hydroxyl group, around 1400 and 880 for carbonate ion peaks, as well as the presence of phosphate ion peaks at around 1030. The FTIR spectra showed characteristic peaks corresponding to calcium phosphate compounds, confirming the formation of a mineralized layers. When comparing the FTIR spectra in distilled water, no hydroxyl stretching bonds were observed, indicating a lack of hydroxyl groups due to no water contamination. In conclusion, this study successfully fabricated calcium silicate and Chitosan scaffold with potential hydroxyapatite formation. The analysis conducted also showed potential bioactive layer formation. As for recommendations, future research should focus on optimizing the ratio of calcium silicate with Chitosan to enhance the scaffold properties. Conduct long-term bioactivity studies to match scaffold degradation with bone formation. implement in vivo testing for biocompatibility and clinical potential, and also utilize X-ray diffraction XRT for deeper insights into scaffold crystallography. That's all from me. Thank you.